Welcome back to CS395. I am Nihal speaking, and this week we're going to be talking about shellcoding. You're probably wondering, what is shellcoding? Well, normally our goal as hackers is to be able to manipulate a binary executable file to execute some code that it shouldn't be executing. Usually our goal is to get some kind of shell prompt that allows us to type in whatever commands we want it to type. And in order to do this on Linux, you have to execute the /bin/sh file. But normally most vulnerable programs won't just have a function call to this file. So we can't just, execute that file automatically. We need to actually write our own code in assembly. And what we're going to be doing is we're going to take this code and we are going to inject it into a vulnerable program. Next week, we're going to go over a buffer overflow. And during this buffer overflow, we're going to take the shellcode that we generate this week and inject it into a vulnerable process. But for now, we're just going to focus on how do you build this shellcode and how it works. Typically, what we want to do is we want to make a system call to the sysexecv function. x86-64 assembly allows us to create system calls, and whenever the OS sees a syscall, it's immediately going to allow the kernel to take control over the program. And once that happens, the kernel will do the function. So just to show you what I mean, here are a list of function calls that are given to us by Linux. You can see that in assembly, we have these functions right here, and each function has a function number that must be given in RAX. And the function parameters are given in RDI, RSI, RDX, and so on. The function that we're most concerned with is sysexecv, which is right here. It has syscall number 59, and it takes in 3 parameters: the file name, the arguments, and environment variables. We don't have to worry so much about these 2 arguments because we're only going to be executing /bin/sh to get a command prompt popping up. These 2 arguments can be set to null. Let me go back to the slides real quick. So right here, this is what we need to happen in assembly. And what we're going to do is we're going to write some assembly code that does all of this. It's going to put 59 in RAX, put a string in RDI for bin/sh, and set these 2 values to null. And then it's going to issue a syscall. When the syscall occurs, the operating system will take control over the program and execute this file. So this is what the shellcode will look like. If you go into basicshell.asm, you can see that this is the shellcode that I've written. So what's going to happen is we're going to move 59 into RAX. We're going to move 0 into RBX to set it to null. And then we're going to push RBX. And the reason we're doing this is so that we can get a string terminator onto the stack. Once we do that, we have these ASCII characters right here. This is /bin/sh written in ASCII. And it's also written backwards. Just to prove it to you that it is, in fact, written in ASCII, I will do 4x in /bin/sh.encode. And you don't have to know this, by the way. This is just something that I'm showing you real quick. And if you want to be able to convert stuff from hex from a string into ASCII, this is the easiest way to do it, in my opinion. Just open up Python and write these 2 lines of code. What you can see is we have hex 2f, hex 62, hex 69, and so on. If we go back to the code real quick, you can see that we have 2f, 62, 69, and so on. Notice that it's being written in backwards order. That's because this is stored in little endian format. So just keep that in mind. We're going to move that into RBX, and then we're going to push RBX so that we have this string on the stack now. Once we do that, we can get a pointer to that string in RDI just by moving RSP into RDI. RSP is going to be equal to the string at this point because we just pushed it onto the stack. Once we do that, we can set RSI and RDX to null just by doing that. And then we can issue the syscall itself just by writing syscall. All right, so that is how this shellcode works. What's going to happen after that is we need to compile this shellcode and then run it, test whether it works or not. So to compile it, we're going to be using this NASM command right here. We're going to be using the ELF64 format. Our output file will be basicshell.o, and our input file is basicshell.asm. So we do that, and this is going to create an object file called basicshell.o, but it's still not an executable file. We still have to link the file in order for it to be executable. So link the file, we use the ld command. And this is the command syntax. This is our output file, and this is our input object file that we just created in the previous command. We hit enter, and now we should have this basic shell program that we can execute. So let's go ahead and execute. Whoops. Sorry, I was doing something earlier. That's the wrong file. This is the correct file. Once we execute this file, we can see that we do in fact get a shell. So we can, this is a typical shell. We can do whatever we'd like on this shell. So this slide just explains some of the commands that I just used. So the next thing we have to do is we have to create an object dump of the files. So to do that, we just use the objdump command. And we're going to be using Intel syntax here because that's what we typically use in this class. So as you can see right here, this is our program, and these are the bytes that correspond to each line of code. So these bytes correspond to this line of code. These bytes correspond to this line of code. And these bytes right here, this is our actual shellcode. This is what we care about the most because these are the bytes that next week we're going to inject into the process once we do our buffer overflow. All right, so to obtain the shellcode bytes, there's a command that you can use to obtain the bytes all in one. And that command is on the slides. You just do this command and replace the file name right here with the file of the executable. And we get the bytes right here. So if you read this, we have B8 3B0000000. That's what we have over here. And at the end, we have 0F05. Same thing here. So these bytes correspond to these bytes. And these are the bytes that we care about the most. This is what we're going to be injecting next week. All right, so there are a few problems with the shellcode that we just created just now. It works when we execute it, but if we actually try to inject this into an actual exploit, then it would not work. And the reason why is because there are null bytes. So these null bytes are going to be interpreted by most C programs as string terminators. And what will happen is when the C program sees these null bytes, it will just cut off the rest of the shellcode. So if I just go back to the shellcode real quick, what I'm talking about are these bytes right here, these zeros. Zeros are going to be interpreted as null bytes. And as soon as we try to inject these bytes into any program, most programs will just cut off everything that comes right after that. So what will happen is we inject B83B00, and then it just sees those two zeros and ignores everything that comes right after that. And we don't want that to happen. So we call these null bytes bad characters because these are characters that should not appear in our shellcode. Null bytes are the most common bad character, but there could be other bad characters as well. At the bottom of this slide, it says there's a networking application that uses hex 59 to indicate the end of a message. There's nothing particularly special about hex 59. It could be hex 50, hex 60, hex whatever. It's just that's the byte that's being used to indicate the end of a message has occurred. And if you had an application like that, then you would also have to avoid using hex 59. But in the programs that we're going to be exploiting next week, we only have to worry about null bytes as our bad character. So for now, we're just going to focus on the null bytes. So what we have to do is we have to figure out why these null bytes are occurring, and more importantly, how do we get rid of them? So let's just take a quick look at the assembly code right here. We can see that there are null bytes on this line right here. This is a move instruction. Same thing over here. We have we're moving the 0 into EVX. So because this is a 0, that's going to cause some null bytes here. This is going to be, there's going to be null bytes here, even though this isn't 0, because EAX must have four bytes of values inside of it. EAX is a 4-byte register. So that's why we must have 4 bytes of values. So when we do this move EAX hex 3B, what assembly is automatically going to do is it's automatically going to append these null bytes at the end, because it assumes you mean hex 0000003B. By the way, this is all little endian format. So when it interprets this, this is going to be the smallest byte, the small little order byte, and this is going to be the higher order byte. So it's not going to change the value of this integer if we append these zeros here, but it is still going to happen because these EAX must have 4 bytes inside of it. We can also see a null byte that's over here. This is happening when we're moving our string back, our string into RBX. And if you look at this string, we have 1, 2, 3, 4, 5, 6, 7 bytes inside of it. But we're moving it into RBX, and RBX is an 8-byte register. So it's going to automatically append this null byte at the end. And we also have nulls here for the exact same reason, because we're trying to move 0 into a register, and it's just going to fill it up with zeros. So these are some things that we have to take into consideration when we're dealing with our shellcode. So how do we solve this? There are some ways that we can avoid using null bytes in our shellcode just by switching around a few of the things that we're doing in assembly. So instead of doing move 0 into some register, we could just XOR the register by itself. And what will happen is when you XOR something by itself, it's always going to be equal to 0. Another thing we can do is we can XOR it by itself to make it 0. And then we can just move the amount that we want into a smaller register. So like we would use AL, for example, instead of using RAX. And if we wanted to move even more bytes, we could shift the register left and then move even more bytes into the smaller register. So to show you what I mean by that, let me go show you the better shellcode here. And this is slightly more complicated than the last one. So I'm just going to open up the other shell so that we can compare the two. Right here, in our original shellcode, we just moved 59 into RAX because that is the Syscall number for exec. Over here, instead of just doing that, we are going to clear out the register by XORing it by itself. So what that means is we just set it equal to 0. And then we're going to move 59 into AL. So AL is the low end byte. And because 59 only takes up 1 byte of memory, we just have to move it into that 1 byte. And now we won't have those zeros being appended at the end because we're moving 1 byte, 1 data byte into 1 data byte. We're going to push the string terminator onto the stack. What we did last time is we moved 0 into RBX and then just pushed RBX. What we're going to do here instead is we're going to XOR RBX by itself to set it to null and then just push it. So pretty self-explanatory. We're doing the same thing as we did over here, except using XOR instead of move. Now, when we try to push this string onto the stack, it's going to get a little bit more interesting here because last time what we did is we just moved the entire thing into RBX, but as we know, that caused a null byte to appear at the very end, and that appeared in our shellcode, and we don't want that null byte to appear in our shellcode. So we can't just move the entire thing in there. We have to make sure that we're moving the exact same number of bytes as it is the register size. So if the register is 4 bytes, we must move 4 bytes into the register. If the register is 2 bytes, then we have to move 2 bytes into the register. So what we're going to do is we're going to start off by just moving the first part of the string into EBX. So as you can see right here, we start at 6A and go into 6E. In case you're wondering, that's this part right here. So we're starting off with the very first 4 bytes, and we're just going to move that into EBX. Then what we're going to do is we're going to shift RBX by 16 bits, which is going to be 4 bytes. So we're going to move all of these to the left by 4, and I'm going to show how this looks in GDB in a moment so that you can have a more visual way of what this is actually doing. So just bear with me if you don't completely understand what's going on yet. But once we get these bytes in there, now we have to get the rest of the bytes in there. So we're going to move 6962 into BX. 6962 are these 2 bytes that are right here. So they're the next 2 bytes that come along, and we're going to move that into BX. BX is a 2-byte register, so we should be good moving these 2 bytes into BX. We're going to shift this left by 2 bytes, and I believe I said 4 bytes here. I actually meant to say 2 bytes. Sorry about that. But we shift RBX by 2 bytes to the left, and then we're going to move 2F into BH. BH is a 1-byte register, so that's going to get the entire string into the register without adding any null bytes into our shellcode. Now, there is a slight problem here. If you look at the text, it says RBX is now equal to \x00/bin/sh. So what this means is that there is a single null byte at the beginning because we moved this into BH, but BL, which is the lower end bit, or the lower end byte, excuse me, is still going to be a null byte because we just shifted. So we have to keep that in mind. And once we push RBX and do the move RSP into RDI, we have to add 1 into RDI just so that we can get rid of that null byte in the beginning. And so now it's going to be equal to the string itself. And if you're confused by this, just bear with me for a moment. I'll open this up into GDB real quick, and you can see exactly what this means in GDB. So to make these values null, again, we just XOR them by themselves just so that they're 0, and then we can do the syscall right after that. So that's a lot of code right there. And I am now going to open that up into GDB, but first let me compile it first. So compiling is the same syntax that we used earlier, except we're now using bettershell.asm instead of basic shell. Then we are going to do LD, and these commands should be in the slides, so you should have access to them. Once we do that, we can run better shell, and we can see that we do still get a shell, so it still works. So let's open up better shell in GDB just so that we can see what it looks like. So we're going to set a breakpoint at start. In case you're wondering, let me open this up. So start right here is where we begin execution, and this is a global symbol, so we can just easily set a breakpoint just like that. In case you're wondering where I got that underscore start from. So we're going to set a breakpoint there. Once we do that, we can run the program, and this is our first line of code. So we XOR RAX by RAX to make it 0. By default, all the registers start off as 0, so I guess it doesn't make too much sense to XOR it right now, but later on, when we inject the shellcode into a running process, what's going to happen is these register values could be whatever, and we don't really know what they're going to be at first. So that's why we have to make sure that it is 0. So use the SI command to step by a single assembly instruction, and we XOR that. We move hex 3b into AL, so now RAX is equal to hex 3b. We set RBX to 0, and then push a string terminator onto the stack. Now we're going to start off by moving the string into RBX. This is where things get weird. So we move this into RBX. This is what RBX looks like now. And then we're going to shift it left by 2 bytes. So when we do the shift left, you can see that these 0 bytes come up here because we did the shift left. So we have 2 extra bytes that are at the end here. And when we do this move instruction right here, we are actually moving these values into these 2 extra bytes that are here. So let's just do that real quick. And as you can see, the zeros turned into these hexadecimal values that we had over here. Now we're going to do the shift left once again. And we once again create 2 bytes. And then we move hex 2F into BH. And because we're moving it into BH, it's going to be moved to these 2 bytes right here, these higher end bytes. It's not going to be moved to BL, which is these lower end bytes. So what's going to happen is we're going to be left with this extra null byte at the very end. When we push this onto the stack, now RSP points to this null byte right here, which we don't want, because if we're running a program and the program sees a null byte, that's going to be interpreted as the string terminator. So that's why we must add 1 to RDI after setting RDI equal to RSP. And if we look up here, we can actually see that RDI is now pointing to our string. So everything's working just fine. And we can do the XORs and do the syscall, and you can see we get a shell. Still a little note about running shells in GDB. Sometimes there are some bugs and issues that occur when you try to run a shell in GDB. So just keep that in mind. If you execute the syscall and for some reason it throws an error or something in GDB, but it works outside of GDB, don't worry, because GDB can sometimes act a little bit weird when you're dealing with this kind of stuff. But anyways, let's just exit out of that. And so we've been able to create this better shellcode now. And let me just print out the object real quick so that we can confirm that there are no nulls in there. So as you can see, you can look through this whole thing and you won't see any 2 zeros sitting right next to each other. There are no null bytes here, which is good for us because when we extract the shellcode, now there won't be any nulls, and now the string will not be cut off when we inject it into the process next week. So there is one more way that we can make the shellcode a little bit better, and that is it has to do with the input redirection command. So normally when you do input redirection, you would do something like /command and then an arrow and then like a file, right? If you're unclear on what I mean by input redirection, basically, when we run this command, it's going to be using this file as the input file. So if you run, for example, head, and then we use shell.asm as the input file, it's going to, sorry, this can have a dot in front of it. It's going to run the head command using this file as the input file. So that is what I mean when I'm talking about input redirection. And input redirection can be very, very helpful when you're developing your exploits, because what you can do is you can print out some hexadecimal characters into a file, and then you can use that file as input. And that's a lot better than just trying to type in hex values into your command prompt, because that's going to be a lot more rougher You could try to use something like Python or Perl to print out hexadecimal values and then put that into a process, but it's much easier to just print them out to a file. So what's going to happen is if we try to use the input redirection command on some vulnerable process, when we do this exec v call, it's going to try reading input from that file that we used instead of trying to read from our keyboard. And that's an issue for us because a lot of times we want to be able to use the input redirection command, and this prevents that from happening. So we're going to need to write some extra assembly at the very beginning of our code. And what this is going to do is it's going to close whatever the current standard input file is, and then reopen standard input to read the keyboard input instead of that file. So just to recap, in case you didn't understand, if we have a program like this that's vulnerable and we wanted to give it some file as input that contains our shellcode, then what we want is we want this file, or sorry, we want our shellcode to not be affected by this input redirection command. And we want to still be able to type stuff in. And the way we do that is we close this file and then reopen STDIN. So there are two more syscalls that we need to be making use of in order for us to accomplish this. The first syscall that we're going to be making use of is sysclose. And what this does is it will close whatever file is currently in STDIN, or whatever, it will close the file that you give, the file descriptor that you give it. And so we're going to give it the file descriptor for STDIN, which is 0. And we're going to just close it like that. Then what we're going to do is we're going to call sysopen, and that is going to open /dev/tty, and /dev/tty is an alias for the keyboard input. And that is how we're going to be able to retype in stuff back into the process. We're going to be opening it up in reading and writing mode, so that way we can both read stuff from keyboard input and also print stuff out to command prompt. So closing STDIN, this is pretty simple. You just have to XOR RAX and XOR RDI and move the syscall number into AL and then just use the syscall. So since going back here, since sysclose takes in this file descriptor in RDI, we just have to give it 0 in that file descriptor, and 0, as I said earlier, represents STDIN. So should be enough code for closing STDIN. Opening this file right here is a little bit more complicated because once again, we have to deal with this string. So what we're going to do is first we're going to push RAX. RAX is going to be equal to 0 at this point. So we can just push that string terminator onto the stack right there. Now this /dev/tty, this is exactly 8 bytes. This is an 8-byte string. So we can just move this entire 8-byte string into RDI all at once because it's the exact length that we need it to be. And when we do this, the compiler won't automatically add those extra null bytes at the end. Once we do that, we can push that string onto the stack. And to get it into RDI, we can push RSB and then pop that value into RDI. This is the same thing as doing move RDI RSP. This is just another way of doing things. To get a null byte onto the stack, we are going to push RAX onto the stack and then pop RSI. And the reason we're going to do that is because these two lines are equivalent to doing move RSI 0. You could also do XOR RSI RSI. Again, this is just another way of doing things. I wanted to show you multiple ways of doing things, and that is why I did it this way. The flag for reading and writing is hex 2702. So we're going to move that into RSI. And then we're going to move hex 2 into AL, which is the syscall for, it's the syscall number for opening a file. And then we just do the syscall itself, and we should be good. So this is our final shellcode. If we go back to the VM real quick, you can see that we have this shell.sm file. And when we open it up, you can see that it contains all of the shellcode combined. This is the stuff that we just went over, and then this is the old stuff that we did a little bit earlier. And this is the best shellcode that we can get for opening up a shell. So we compile this once again. And then run it. And as you can see, we get a shell, so it works. If we do an object dump of it, you can see that there are no null bytes here. You can go through this entire thing and you won't find any null bytes. And we can do that for loop command that I went over earlier, extract the exact bytes from it. And this is what we're going to be injecting into the process next week. So keep this handy because we are going to need these bytes next week. All right, so your homework for this week, you do not have any write-ups due this week, but I do want you to create the shellcode for executing /bin/sh. Please do not skip this because we are going to be using these bytes for the remainder of the course. I also want you to read this article right here. The website that it was written on, it looks kind of cringe, but it has some really good content on it, and it really explains in depth how a buffer overflow works. You don't have to read the entire thing because it's very long, but I just want you guys to skim through it so that you have an understanding about what we're going to be doing next week. All right, that is all that I have for you today. Thank you for watching.